There we go. Okay. Okay, so either equation is fine. Either one. They're exactly the same thing. And the question is, how do we get the graph in Desmos? So you just type that exactly. So the problem is finding the picture sometimes in Desmos, and I'll show you how to do that. So you would do y equals negative 100x plus 6,500. Now you can't see it, right? Like I don't see the equation, and it's because the y-intercept, as you noted before, oops, that's not what I wanted. The y-intercept is 0, 65. Where's my comma? 0, 6,500. So where is that? Well, if you look at the scale on the graph I have, the largest y value is 6, and we got to get to 6,500. Like, that's insane, right? Like, we're not anywhere close to it. So click the graph settings button in the top right corner, and you can see a scale here. So the x-axis, we're going from -10 to 10. The y-axis, we're going from negative this to 6.6. Well, we don't need negative numbers, so I'm going to change the y-axis for a 0. And then we need the y-axis to be close to 6,500. So I'll do 7,000. Oh, there's my line. But you can see it's not a great picture. I need a little more of the x's. So let's make x go from 0 to 100. Hey, there we go. Now I can kind of drag around and I can see a complete picture of this line that I've graphed. And I can see the x-intercept and the y-intercept, blah, blah, blah. What do you think, Jennifer? Is that?
Yeah, that's helpful. I just literally like put in the points for each year until I said that that was enough.
You only need 2, and then you got a line. Now, here's the thing. I don't particularly care about you drawing by hand. Like, what I mean by that is, like, where is this? What you would have written on here, this might upset you, Jennifer, and it's totally fine for you to be upset at me. Yeah. And I understand it. You can just be like, hey, here it is. It's going to hit right here. It's going to hit right here. And here's my graph done.
Okay.
Because why would I care about your hand-drawn graph that's difficult to draw anyways, when you can get this perfectly drawn one right here, right? Like, yeah. Ugh. So anytime there's something that says draw the graph the equation, and draw a rough sketch, I do mean that. I mean, I want to make sure you can get the information from here and then just prove to me you saw the important stuff.
Okay.
So really good question. There's the place where this shows up again is going to be right here. Question D. Well, I didn't ask you to draw it, so never mind.
All right.
Cool. Good question. Other questions you'll have. I'm happy to entertain any questions that anyone has.
Were we supposed to do that practice quiz? Like there was, I don't know what it was.
Okay, yes. Look at you. You're like miles ahead of and doing everything that's in Canvas, aren't you? So I need to fix that. What that is a way for you to experience the lockdown browser for when we take the midterm in the not too distant future, but still a little bit distant yet. And so the purpose of that quiz is not for a score at all. It's to work the lockdown browser. And I don't even think, did it lock down your computer when you took it?
I didn't take it. I was just asking if you were supposed to.
Oh, that's an even better question. Yes, but not yet. I've got to flip some switches and make some things happen. Thank you for asking that. To make it so that it actually does what I want it to do, and that is to test the software so that you can take the midterm. What is this week? Are we in week 5? Is it week 6 already?
Also, we did do 2.5 last week. We're on 2.6.
Okay. Nice. Yes, this one right here. So this is the one. You were just doing it. Do you have the project done too?
No, I have it a little bit started, but
Ooh, look at you. Good job. Do you have questions on it?
not yet.
Okay, nice. Oh, it should allow you to take multiple attempts. All right. Someone else asked about multiple attempts. Yes, I need to mess with this still, and yes, good questions. Okay, so we did do 2.5. Wonderful. Did we look at the 2.4 worksheet then? Have you all done this problem? Did we do this, or did we run out of time?
I think we did that together.
Okay. All right. Well, now that we've got that cleared up, let's do 1.6, unless there's other questions. Okay, so now we're going to learn about exponential models. Actually, we're just going to learn about exponential stuff first. And then we're going to learn about exponential models, how to find them. And we're going to introduce a special type of notation called function notation, and it's super useful in Desmos. And when we say notation, we really just mean the way to write something. If we were to think about how that would show up like in a English class, notation in math is like a thesaurus in English. Because like you have a special word and we want maybe a different word that expresses whatever you're trying to express a little better. So we go to the thesaurus and find synonyms, another word that's similar, and then we use that word instead. In math, this is the same thing. When we talk about a particular type of notation, it's a different way to write something. Sometimes it's helpful.
When you guys went over 2.5, was that not recorded? Because like I'm looking at the YouTube video right now or whatever, and we go through like the 2.4 worksheet, but then you go to talking about the project and we didn't touch on 2.5 like at all from what I'm seeing.
Okay, so what was the last day we were in class? I probably just uploaded the wrong thing. We were in class on the 5th.
Yes.
So it should have been the 10.5 video.
Yeah, that's the video I'm on.
Did I just not record it? 10.12, that's the one we're working on. 1:30, 10.5. Are there two videos here? Here's the video. Let's keep the sound off so we don't have to listen to me. Sorry, everyone that, listen to me apologizing. Do I say that a lot? So at the beginning, it looks like, yeah. So at the very beginning of the video, this is the 2.4. Apparently I didn't show. So yeah, they were doing that. So is it not matching on YouTube?
Yeah, it shows that, but not 2.5. And I'm
No, this is I'm sorry, this is 2.5.
Oh, okay, because I was like, I was at this class, like I missed a whole section. How? So okay, so we're working on 2.5 then.
So this now I'm super confused. So that is what you're seeing in those videos is the 2.5. That's this. So that first data set was the total fat and the calorie stuff. So that was 2.5. And then the 2.4 worksheet from the course pack corresponded to the 2.5 content in the textbook.
So what does worksheet 2.5 correspond with?
2.5 and 2.6. So
Okay,
the chapter 2 numbering stuff is all screwed up. It's just it's messed up.
okay.
Okay. Whew.
I'll try to figure it out then.
Did you get the 2.4 worksheet done?
Yeah, 2.4 is done, just not
Okay.
5. I haven't
So,
started.
and that's the way it should be, because the
Okay.
first part of 2.5 is linear stuff. The backside of 2.5 is exponential, which is in section 2.6.
Okay, all right. Thank you. I just
So
thought I was
no,
missing
you're
the
good.
whole thing.
You're good. This is on me.
All right.
Okay, so let's learn exponential stuff. And then I think at the end of this, or tomorrow, or I mean Monday, maybe we'll write up a nice overview of the whole chapter, and it's just linear and exponential stuff. Okay, so we'll quick label these things that we know. So linear growth is adding a constant. It can be positive or negative. Well, if it's growth, it has to be positive. So it's adding a constant. We call that thing slope, and it has an initial value. And the amount we add never changes. So that's what we knew before. We also know a ton of other stuff already. And then exponential growth is we're multiplying by a constant. And we don't know a special name for that yet. We're going to learn that today. And then the values get larger and larger over time. So the amount, it gets big fast. That's the big difference between the two, is this multiplying and adding. And what's funny is multiplication is just repeated addition. So I don't know if that's funny. Okay, so here we're looking at a table. We've got a $15,000 winning from a game show, let's say after taxes, and you've decided to deposit it into an account. And so what we're going to do is look at these. We don't know what this investment, how it grows. We just know this is happening, and this is the look of it. And we should just glance at this and state, oh, that doesn't look particularly linear, right? There's a curvature to this line. And so we probably already know it's not linear, but let's do some of this stuff. So first, for each value in the table, after this initial investment, after our 15,000, so everything after, divide the amount by the value of the account the previous year. So 16,050 divided by 15,000. This divided by that. Do that. Do it in Desmos and see what you get. And then see what that says about it. So I'll give you 5 minutes to try that. Set a timer for 5 minutes. Probably too much time, but try it out. Okay, y'all, what numbers did you get? Or were you like totally lost? Ooh, nice. Was that true for every single one of them? And now I'm answering the question because I'm actually typing it out. At some point, you're like, "Oh my goodness, I see there's a pattern here." It's not exactly true, I guess. Yeah, nice. If rounded up, definitely. I mean, if you look at how many decimal places you're rounding to on that one, it's like, yeah, most definitely. Do you remember doing this already? Do you remember when we did this? Does anyone remember? Oh yeah, here's a rounding one. Another rounding one. Whew, here's the 5-minute timer. So this is what we did at the beginning of chapter 2 to determine if something was exponential or not. We were dividing the next value by the previous value. And if the number was the same, we called it an exponential situation. So the answer is it's 1.07 approximately for each step, for each of these comparisons. And that tells us this is exponential growth. And another way to think about this is this number we found is what we multiply by to get the next. Sorry. Ugh. It's the number we multiply to get the next one. So if I go to this line 6, year 6, and I take that 22,510.96 and multiply by 1.07, I get the 2486.72. Yeah, it rounds up to 73. So someone did some bad rounding here, apparently. Okay, so now find the relative change. Does anyone remember the relative change formula?
Isn't it new minus old divided by new?
Close. You were killing it. New minus old divided by,
Old.
these have to match. I don't know why I made that noise.
Okay.
Excellent. Yes. So try that for a couple of these. So like 0 and 1, 1 and 2, 2 and 3, 3 and 4. Let me give you 3 minutes to try that. Set a timer for 3 minutes. All right, what number did y'all get? Actually, what numbers did you all get? Ooh, I think, Mike, that's you, right? You got 0.07. And if you remember interpreting the relative change in context of the situation, Mike, you're crushing it. The value increases by 7% per year. Now let's pause and let's look at, yes, Jennifer, yes. Let's look at what's the connection between what we got here and what we got here. Do you see the connection? So when we did the next number, 16,050, divided by the previous number, we got 1.07, the number we multiplied by. There's a 1 added to it. Okay, what's the 1 represent? Itself. And as a percentage, what is itself? You nailed it. This is the 100%. This is the 7%. Right? Yeah. So if we converted this number to a percentage, we would say 107%. We talked about this in class a couple times before, and I think I was confusing people on how I was talking about it. We're seeing a 7% increase year to year, meaning if this is a savings account, that's the interest rate. The number itself is 107% larger each year. Right? So one of them is the number we multiply by. The other number is the percent we're adding in. Whew. Okay. Can you find the value of the account after 10 years? Our author is giving us a hint. We need exponents. This is what I'm suggesting you type into Desmos. 15,000 times 1.07 10 times, or raise it to the 10th power. See what you get. I'm getting 29,507.27. Okay, now we want to turn this into an equation. So we want to write an equation in the form y equals some sort of expression. So y is going to be the value of the account. It's going to equal something that has an x in it that takes into account the years. So notice how I wrote it here. I'm just going to copy this, and instead of the 10, I'm going to put an x in there. And this is the account value after x amount of years. So we're to verify that this works. Well, let me show you a trick in Desmos. We want to show that this gets us the exact same values as what we got here. So we're going to do what we did. I need a new graph. No, I just need a new blank graph. We're going to do what we did with Jennifer at the beginning, right, where we type the equation in. So I'm going to type y equals 15,000 times 1.07 to the x power. So I'm going to do shift 6 for the exponent x. If you're wondering how to get that x in the exponent, if you're using your phone, you would open up the keypad and click this AB button, and it'll raise it as an exponent. Now what I'm going to do is I'm going to convert this thing to a table. So I'm clicking, let me go full screen. I'm clicking this gear button that says edit list. And here it says convert to table. So I'm going to click that. I don't need these values. And I'm going to type in the values we want. 0, 1 year, 2 years, 3 years, 4 years, 5 years, 6, 7, 8, 9, 10. We didn't need all of those, did we? How many did we need? We needed up to 7 years. And so now we can see that our tables match 15,000, 15,000, 1650, 1650, 17,173.50, blah, 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 blah. So that equation did do what we wanted it to do. It's creating this table of values. And if you know what's happening here, that's exactly what our author did to generate this table. Okay, has everyone got that? Everyone able to get that table and confirm the two? Okay, so now we're going to talk about function notation. So our author gives us a definition. I'm not particularly worried about this definition so much. Maybe I should be. A function is a relationship between two quantities where each input produces a unique output. I'm not so worried about that. For now, what I want you to note is the notation. So our author gives us the equation here. F of x, this is how it's read, F of x, as our author's noting here. It doesn't mean F times x, just means F of, and that's equal to 15,000 1.07 to the x power. So all we're doing here is we're replacing the letter y with f of x. In other words, we're saying that y is equal to f of x. Those two things mean exactly the same thing. It's not even there, it's even a stronger thing than synonyms. They are the same. What's different now and how we use this is we can plug numbers in. Like if I want to know after 100 years, what's the value in account balance, what I would do is write f of 100, and that tells me take whatever's in the parentheses and plug it into the variable of x. That's why we say f of x. So that just says do this. Now you might be thinking, okay, how is that really useful, right? Couldn't you just say let x equal 100, find out y? You're right, we could do that. But here's what's cool about Desmos in this notation. What I can do now is I can go to Desmos and I can type in my function. So I'm going to get all this out of here. And I can type the function just as it's written there, f of x equals 15,000 times 1.07 raised to the x power. All right, so there it is. You don't actually need any of these parentheses. Let me get rid of them. There we go. And I can type in f of 100. Whoops. And it spits out the answer. Maybe I want to know how much is in the account after 50 years. Well, I just type in f of 50. And it does the calculation for us. So it's more or less a time saver, right? So we don't have to keep writing this out. I could also create a table, and in the table, I could write f of x1, and then I could start generating a table by plugging in numbers here based off of the function that I've defined here. So Desmos ties all of this together, and we can, it becomes super cool. How we doing? Is everyone able to do that? Let me pause here and make sure you're following and that you've got that, you're able to get that stuff typed in Desmos. So are you all able to get that in there? I'll just assume you can. And let's go down here. So here it says find f of 12 and describe what it means. So do that. Find f of 12 and tell me what f of 12 means. All right, do this. I'm going to force myself to be quiet for 3 minutes. Set a timer for 3 minutes. Y'all get the number for it? What's f of 12 equal? I got 33,782.87. Okay, talk to me, Jennifer. What's happening? Let me clean up just the stuff we need. You need this and then this. Oh, when you try to do a table. Oh, okay. Yes, let's talk about that. So to get the table, oops, not expression. To get the table, ugh, stop that. Notice this says X1, and then I'm going to replace this Y1 with F. But what I put in parentheses has to exactly match what's listed here. I'm guessing that's what's wrong. So you have to type in X1. Like if you change this to X, does it work with X? Yeah, it'll work with X2 or just X. It defaults to X1. And then that's how you would get the table. Does that fix the problem for you? Okay, perfect. Yeah, that's an easy, it's an easy thing to mess with. Good. Okay, so we've got the number F12 equals 33,782.87. What does this number mean? Well, it means after 12 years, the value is 33,782.87. That's what that means. Okay, cool. So now what we're supposed to do is we're supposed to look at the graph, like what's happening as we move left to right. The value is increasingly The value is increasing faster over time, right? If it was linear, the increase would stay the same and look like this. But as we get further and further out, the value gets larger and larger and larger, faster and faster and faster. So let's test that. The author says, how much interest would you earn from 0 to 5? Year 5. Well, you're going to calculate the difference between those amounts. And here's what's so awesome about function notation in Desmos. If I want to know how much interest was earned, I just need to take f of 5 and subtract from it f of 0, right? Because f of 0 represents the amount of money you put in. You put 15,000 in the bank account. Here we are at year 5, you've got 21,000 in there. If we take out the amount you put in, you get the amount of money the bank gave you. Well, notice how I wrote that. I didn't have to rewrite things a bunch of different times. I just did f of 5 minus f of 0, and I got 6038.28. That's the amount of interest. The author says use the formula for the function, but the table of values is better. Absolutely not. This is so much better. Well, then look, it says, well, what about years 35 to 40? Well, same thing, right? If I take f of 40 and subtract from it f of 35, I will get the amount of interest earned between those 2 years. So let's do that. F of 40 minus f of 35. Whoa, 64,468.15. Note, this is over a 5-year period, and this is over a 5-year period. Huge difference in earnings. Why? Anyone know why there's so much difference?
Is it because it's compounding interest?
Yeah. Yep. We're earning 7% each year. So in the beginning years, the amount of interest, like the 7% off of the previous year, it's a small amount. Whereas when you get to 35 and 40, the account balance is way higher. Let me just go to my table here. Let's put a table in real quick and we can see that. F of x1. So if we do year 34, there's 149,000, and then in year 35, there's 160,000. So we're earning to get to year 35, we're earning 7% of 145 or 149,000, right? Roughly. So the balance is so much higher. Okay, awesome. Check out this next one. Now we're going to look at what's called exponential decay. That was called exponential growth. And the account balance got larger and larger over time. Now we're thinking about what happens if the value is getting smaller over time. So do the same thing. Calculate the relative change. This is new minus old divided by old, and see what number you get for all these. By the way, notice if we're doing it between 0 and 1, the new value is this one and the old value is that one. Let me give you 3 minutes. You see if you can't find out what these numbers are. Okay, Jennifer, nailed it. Yeah, it's negative 0.2 for all. Can you interpret that number in context? So in context, what we'd say is the amount of caffeine is decreasing by 20% per hour. So we'll just say caffeine. Nice, yes, is decreasing. That takes into account the negative by 20% per hour after you drank it. All right. So we know that a quantity is either exponential or exponential growth or decay if the relative change value is constant. That's what number 3 is supposed to be. Relative change is constant. Here it was negative 0.2, blah, 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 blah. That's the relative change there. And then back in this other problem, it was positive 0.07. Yeah, right. Not this number. This is a different number than the relative change. This number right here. That was constant throughout all of these when we rounded to the appropriate amount. Okay. So now we got to figure out what does it look like, right? We noticed this little thing was going like this. So as time increases, the amount decreases. And it starts a really fast decrease, and then it seems to taper off. So if you think carefully about this, what's the multiplication factor that you need to multiply the previous hour to get the next? So what am I multiplying 180 by to get 144? Well, let's find it using the next divided by the previous, right? That's how we did it in the previous problem. So it should work here. It will work here. 144 divided by 180. Oh, 0.8. Let's just double check that's true for the next one, just for fun. 115.2 divided by 144. Oh, it's 0.8 as well. Hey, what's the connection between 0.8 and negative 20 or 20%? What's the relationship between those two? I'll just do this. Note 0.2 plus 0.8 equals 1, or 20% plus 80% equals 100%. So when something is decreasing by a specific amount each time, the relative change is a constant negative percentage, then the multiplier factor, the multiplication factor, is 100 minus that percent decrease. So if we're going to write an equation, just like we did in the last one, we'll write it in function notation. We do f of x equals some sort of initial amount. In this case, the initial amount is the 180 milligrams of coffee, or milligrams of caffeine that we started with when we finished our cup of coffee. So that's the 180. So we started with 180 milligrams in our system, and then 80% of that is what remains after each hour. So there it is, right? There's our function. And I'm going to change this from f of x to g of x because I want to highlight that the letter we use to write function notation doesn't particularly matter. What matters is the letter in the parentheses with the x. You can see all kinds of letters here. You could do pictures if you wanted. They're just harder to write. So let's get that table in Desmos. I'm going to get a whole new blank graph. I'm labeling my function g of x, and that was equal to 180, the initial amount, times 0.8 raised to the x power for each hour. I'm then going to add in a table, and now I'm going to type in here g of x1. Oops, not divided by 0. And I want 0, 1, 2, 3, 4, 5, 6. I forget how many things did we have? Oh, and 7. So there we have it, not rounded to the same number of decimal places as their table, but nonetheless we can see that this equation or this function matches our table. Okay, now we're going to do a couple problems, right? So here it says, let's take our function and let's figure out how much caffeine is left in your system after this many minutes. Well, this is an x value, except that x is defined as hours after the cup of coffee. We'll say ... So these minutes aren't going to work. So we have to convert those minutes into hours. So the x value here is really 150 over 60. That's converting the 150 minutes into hours. So all I have to do is type this into Desmos. I don't even have to figure out how many hours is that. It's probably not too difficult to figure it out. It's like 2.5 hours, but I'm wanting to demonstrate the beauty of Desmos. All I have to do is go here and type g of 150 divided by 60, and I get my answer. By the way, note that 150 divided by 60 is what I said, 2.5. But this is approximately 103.04 milligrams of caffeine. And that's how much remains in our system. I can't spell caffeine all of a sudden. Oh, it's right there. You know, I could just use my resources, couldn't I? Oops, I wrote down an F when I've defined this as G. It is important that you keep track of the letters. Okay, now for a tough question. We're going to estimate the amount of time needed for the caffeine to drop to 40 milligrams. So graphically speaking, we're going to go to this 40. Looks like it's right here. And we're going to say, well, what is that number? It looks like it's about 7 hours to go from 180 to 4. Well, ignore this. What we're going to do is we want to know if g of x is equal to this 180 times 0.8 to the x, we want to know, when does g of x equal 7? Nope. When does it equal 40? That's what we want to know. Well, remember, g of x is another thing for y. So instead of writing y, or g of x, I'm going to write y. And I'm going to type this into Desmos and see what the picture gives me. So I'm going to type y equals 40. Now, let's look at our graph. Oh, we can't see it. What? Well, we have this nice handy table. So I'm going to do zoom fit. There we go. Here's our g of x function that is modeling the amount of caffeine in our system after X amount of hours. Here is the equation y equals 40. So it's the graph of that constant value. And if I click it, I get the exact amount of hours, 6.74. Well, the best estimate of amount of hours. So the answer here is really approximately 6.74 hours, which rounds to 7. So my estimate above was not bad. You are not going to be able to solve this algebraically unless you understand logarithms. And if you understand logarithms, awesome. Show me how to solve it with logarithms. This is the one, Jennifer, that I was mentioning at the beginning, where you're going to have to know how to type these equations in, because this is the only way I'm teaching you how to solve these. But if you know logarithms, by all means, go for it. Solve it with logarithms.
So for that graph on question 9, did you like put that in there? Because it is not in my book.
Oh, yeah, this graph is he copied it. He should have put it in there from your book. He copied it from here.
Okay.
So he's
All right.
like, wouldn't that have been nice? So you don't have to flip back to where the graph originally was.
Yeah, I was just looking at yours and I was like, wow, I'm missing a whole graph, but
Where did
okay.
that go? Yeah. And what's really more important is that we have the graph here, because then we can use it like we just did. Yeah. Sorry. Okay. Wow, we've done it. We've done it. So let's take a look at the course pack now. What you can now do is you can do all of the 2-5 worksheet. So you've got this first side where you're identifying slope and growth or growth/decay factors. Hopefully you see this is clearly exponential based on the graph, and this is clearly linear based on the graph. You should also be able to do, you should be able to go all the way to page 27. You're not really ready to do 2-6 yet, so don't worry about 2-6, even though that's what we've just did. What I would like to do right now is write a summary of everything we know. Actually, no, I don't want to do that. I want to do that tomorrow or Monday. What I want to do is formalize the exponential stuff. So let me get a new sheet here and let's put this together. So here's the information for exponential. I'm going to call it models. What we're going to do on Monday is look at how to model things. So in 2.7, we'll do the same thing we did in Desmos with the linear models, but now we're going to do it with exponential. So the equation is y equals ab to the x. And in function notation, that would be f of x equals ab to the x. And what I'm hoping you noted, these mean the same thing, is that there are two parameters here. And the first one is the y-intercept. And that's the point 0, a. And we call this thing, what we really mean by y-intercept in context is it's the initial value. That's what this a is. So when we're interpreting things, we're like, hey, at time 0, this is how much stuff there was. But the other parameter is this b, and it is wonky. So let me put it all together. So the first one we looked at is a growth factor. That's the name for it. And that is b when b is a number larger than 1. And what we have connected to that is this thing called the growth rate. I am going to label the growth rate, boy, what should we use for it? It's a percent. Can I use a lowercase p? The growth rate is calculated this way. That little percent is equal to b minus 1. So if we know the growth factor and we subtract the 100% away from it, we get the growth rate. And what this means is it's the percent growth per X units, whatever that is, time, minutes, hours, people, whatever X is defined as. We call B a decay factor, like the problem we just did, if B is a number between 0 and 1. And then we can have an associated decay rate, and it's calculated exactly the same way. P equals B minus 1. The difference is this number will be positive. This number is going to be negative. The other thing to note is that this rate is really the relative change. right? That's where that comes from. So if I were to look at a graph of these two things, if I were to graph, am I writing this too fast, y'all? This is a B value greater than 1. That would be growth. This is a B value between 0 and 1. That would be decay. That's what the graphs would look like. All right, so that's the summary of what we've just discovered. On Monday, we'll put this together with modeling. And then after that, after Monday, you'll be ready to finish the project entirely. So I think we're skipping to 2.8. 2.8, we kind of put this all together with the modeling and all the rest, and then we're ready to go. Okay, any questions you'll have? So what we have, what, like an hour, roughly an hour, a little less than an hour. Wait, do we have a question? Okay, good, Jennifer. We have roughly an hour left of class. I've covered the new material, so I don't want to like force anyone to hang out here and do things. What you should be able to do now. Oh, no, wait, let's do the lesson check. That's the thing I always forget. Let's write that down. And then I'm going to set you loose on working on the stuff. And, you know, if you can do that at a different time, that's fine. I'll hang out here and answer questions and help you through anything anyone needs to talk about until 3. And then I'll turn it off, or until everyone leaves. Either way. Now let's get this lesson check. I forget what that answer is. .6 lesson check. Let's do October 13. Well, looks like I better get it right, because there's not unlimited attempts. Oh, thank you. I have not posted the chart. Let's dump that in there while we're all here, so that you all can get going on the stuff. So this one is, how much entrance will you earn? It's page 211, question 11. That's one of the ones we did here. Whoops, wrong one. This one, nope. Here it is. This is your answer, 60, 38, 28. So this is lesson check 2.6. 60, 38.28. Round to 2 decimal places. Did I get it right? Yay. Okay. Laquita asks a great question. What about the data set that needed for project 2? So let me upload that. And then you can get that data going. Federal outlays by year. Okay, there we go. Okay, there you go. Project 2 data, that's there for you. You put it in the other course as well. Other questions you all have? Other things you need from me? If not, jump on the worksheet and see how much of that you can get done. If you're wanting to stay and work on that and get help from me, if you get stuck.